One of the reasons we make tree diagrams, like you guys already did in your Are You Ready packet, is because they show the total number of possibilities for ways to choose item from different lists. So, the total number. We usually talk about menus and ordering food and how many different types of meals maybe you could plan out. So let's say we're going to lunch and we can either have a sandwich or pizza for our main course. Sandwich or pizza. Once we make that selection, then we can choose a side, soup, salad, or breadsticks. So we could have soup, salad, or breadsticks if we get a sandwich. Breadsticks. Or if we get pizza, we could choose soup, salad, or breadsticks. So the question here is, how many different lunch options do we have? Well, let's count them up. Each of the final branches represents a different meal. So you could have a sandwich with soup, a sandwich with salad, a sandwich with breadsticks. There's 1, 2, 3 options. Pizza with soup, there's a 4th option. Pizza with salad, there's a 5th. Or pizza and breadsticks, that's a 6th option. So you only have to count out the number of final branches. So the answer to this would be 6. Let's see the next example. You should start with having breakfast, and then let's check out what we can get to eat at Tim Hortons. A bagel, a donut, or a muffin. A bagel, a donut, or a muffin. Now we choose something to drink. We can get hot chocolate, coffee, or an ice cap. So, hot chocolate, coffee, or an ice cap. And the same 3 things will come off the other 2 food options. Hot chocolate, coffee, ice cap. Hot chocolate, coffee, and ice cap. So you can abbreviate however you need to. In order to answer the question, how many different breakfast options do we have, we count up the number of final branches. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different breakfast options. What we just did in order to answer those questions, how many breakfast options are there, we could have done much faster if we would have used the fundamental counting principle. Basically, it says if we have a bunch of lists, we just take however many items are in each list and we multiply them together. So M1 would be if there's a first list with however many items, such as having a sandwich or pizza, that would be 2 options. And the rule is you multiply it by however many options there are in your second list. So we had soup, salad, or breadsticks. We had 3 choices. So 2 times 3 is 6. We could have used the same setup for breakfast. We had 3 options of what we could get to eat, and we had 3 options of what we could get to drink, and so sure enough that totaled out to the 9 possible breakfasts. We could keep going and have as many lists as we wanted to, and you would just keep multiplying the numbers together. So to answer the question in the next example, how many different meal options are there for lunch? Well, let's look at how many entrees there are. There's 3. Let's look at the sides. There's 3 sides, so we're going to multiply. And then how many drink options are there? There's 4. So 3 times 3 times 4 is 36. If we would have made a tree diagram, we would have come out with 36 branches, which would have been a pretty big tree. So sometimes, if the more lists you have and the more items in your lists, the fundamental counting principle is just a little faster. What about 1B? Out in Utah, you have a license plate with 3 digits, so 3 numbers, and then 3 letters of the alphabet. All right, so we have to figure out how many digits do we have to choose from. Well, the numbers that we have, like on a telephone keypad, would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and then there's also the 0. So that's a list of 10. So we can choose from 10 numbers in the first spot. It does say that the digits or letters may be used more than once. So in the second spot of the license plate, we have the same 10 digits to choose from, 1 all the way to 0. So we're going to multiply by 10 more, and then for the third number, we'll also be able to choose from that list of 10 digits. Now for the ABCs. There are normally 26 letters in the alphabet, but we're getting rid of I, O, and Q. So let's take those off, and we have 23 letters of the alphabet to choose from. 23, 23, 23. So you're going to multiply all those numbers together, and you get 12,167,000 possibilities. I think that's enough to have none of the license plates repeat themselves. When we work with probability and statistics, a lot of the formulas we need involve factorials. That's the math symbol that looks like an exclamation point. What it means is you take a number, so if we're doing 3 factorial, and you multiply 3 times all the numbers lower than it, times 3, times 2, times 1. We're going to leave out 0, because if we multiplied that by 0, the answer would be 0. And then we just figure that out. 3 times 2 times 1 is 6. Now, you could do each of these by hand. We could write 6 times 5 times 4 times 3 times 2 times 1. Calculate it out. We could do that. We'd get 720. But then we'd have to do that for 10. 10 times 9 times 8. The bigger the number, the more writing and the bigger our answers will be. So in order to kind of save space and time, there's a way to type the factorials in the calculator. What you do is, if we were finding 3 factorial, you type the 3 in first, so you type in whatever your number is. You press the math button on your calculator. It's right below the green alpha button. You press over to the right 3 times. That'll take you to a tab that says PRB. That stands for probability. And then if you look at option 4, it has the exclamation point, the factorial sign. So you pick enter, it'll show up on your screen, it'll look like 3 factorial, and it'll tell you the answer is 6. So if you did 10 factorial on your calculator, you would get 3,628,800. Now for the last one. You might think that 0 factorial is 0. However, the answer to this is 1 if you type it in the calculator. And that's so that if we have to deal with 0 factorial, it doesn't cancel our answer out. So let's try using the factorials in the next examples. The first thing we're going to do is find a permutation. A permutation is when we pick objects from a group when order matters. So what does that mean? Well, in example 2a, we have a club, and it has 5 people in it, and from those 5 people, we're going to pick a president, a vice president, and a secretary. So it matters who does what. So that's an example of a permutation. So let's think about this. We have 5 people. If we're choosing the president first, we have 5 people to choose from. But then we also need to choose a vice president. Well, since we used up one of the people to be president, then we only have 4 people left to choose from. We're using the fundamental counting principle here. We're just multiplying the number of items in our list together. Finally, we have to fill the secretary position, and since we've already used 2 people, we only have 3 left to choose from. So 5 times 4 times 3 gives us 60 different ways we could elect those 3 offices from 5 people. Let's try the next one. This time we have 9 paintings, and we want to hang them on the wall from left to right. We're only going to be hanging 4 of them. So it matters which one comes first, second, third, and fourth. So the first time we go to hang a picture, we have 9 to choose from. That one is hung on the wall first, and then we have 8 left to choose from, and then 7, and then 6. When we figure that out, we get 3,024. And the last one, we have a teacher who's going to send students to the library, the computer lab, and the office. So each student's going to a different place. So we have 3 different places those students are going. There's 28 kids in the class, so the first time the teacher sends a student, there's 28 kids, then there's 27 left, and then there's 26 left. So you calculate that out, and there's 19,656 different ways to send 3 students to those different places. So let's figure out how those calculations match up with these formulas up above here. I kind of skipped that intentionally. If you think about it, what we just did, because we figured that would make sense, is we multiplied the 5 times 4 times 3 in example 2a, and then we stopped because we only had 3 positions to fill. If we kind of rewrote our work using a factorial, if you notice 5 times 4 times 3 is almost like 5 factorial, except for we didn't include the 2 and the 1. So how can we show that we don't want to include the 2 and the 1? Well, you cancel the 2 and 1 out by dividing. If we have a 2 on top and a 2 on bottom, they cancel out. And if we have a 1 on top and a 1 on bottom, they cancel out. So basically what we've done is we've taken 5 factorial and divided it by 2 factorial. In 2b, on the top we had 9 times 8 times 7 times 6, which is like 9 factorial, except for we left off the 5, 4, 3, 2, and 1. So what must we have divided by? Well, we got rid of the 5, 4, 3, 2, and 1. So that means on top it was 9 factorial, and on the bottom it was, see how we start with the 5? 5 factorial. So those all canceled out, and it gave us our final answer. The last one, I'll write this one a little faster. We would have had 28 factorial on top, and then how many would we have had to cancel out on the bottom? Well, you have to think of where we kind of cut the top off, which would be at 25. So 25 factorial on the bottom. And it would have given us the 19,000. So that little formula right there is exactly what we have right up here in the formula box. You take the total number of items you have, put it on top, so like our 28, and we divide it by what we have left after we make our number of selections. So this is the total, and that's the number you take out, or the number of positions you're filling, or whatever you're selecting, your number of selections. So the notation would be NPR. There's N permutations of R. You would write, if we were doing 2C, 28P, and then we were choosing 3 different students. 2B would be 9 paintings. We're finding the permutations of ways to arrange them in 4 positions. And 2A would be, we have 5 people. We're figuring out the permutations for 3 different offices. So that's what the notation would look like for the formula. You can plug it right into the formula and calculate it out using the factorial, or you could type that right in the calculator. In order to do that, let's do this one right here. You would type the 5, and then you would go to math over to probability, and you would pick option 2, and then on your calculator, an N, a P, and an R will show up, and then you type in the 3, and it would give you the answer. What if you're choosing items from a list and the order doesn't matter? Like, it doesn't matter who does what job, it doesn't matter what order paintings are hung up, for example. Then you'd be talking about a combination. For that, order does not matter. I think about it as ordering a combo meal from a fast food restaurant. If you say you want a combo, you can tell them you want a burger, fries, and a drink, or you could tell them you want fries, a burger, and a drink, or a drink, burger, and fries, or a drink, fries, and burger. It wouldn't matter the order you order. It would all be the same food on your tray. So that's kind of what I think when I think of combination. So let's do the 2 examples, and then we'll talk about that formula. Katie is adopting kittens from a litter of 11. So she is going to have 11 kittens to choose from first, and then 10, and then 9. So for this problem, we're not going to stop there. We have to eliminate the fact that it doesn't matter the order she chooses those 3. So to get rid of it, we have to divide by the 3, the 2, and the 1, because it doesn't matter the order she makes those 3 selections. So that's what will give us the answer. If we figured that out, we would get 990 on top, and on bottom we would get 6, and when we figure that out, we get 165. Alright, what about 3B? We have 30 kids in a class, and this time the teacher is sending them all to the same place. So they're all going to the same destination. It doesn't matter who gets chosen first, second, third, fourth, etc. The teacher is sending 7 kids. So for the 7 kids, there's going to be 30 kids to choose from first, then 29, then 28 for the 3rd pick, and then 27, and then 26, and then 25, and then 24. 1, 2, 3, 4, 5, 6, 7. Okay, that would take care of the 7 selections. But then we have to get rid of the fact that the order she chose those 7 doesn't matter. So we get rid of 7 times 6 times 5 times 4 times 3 times 2 times 1. When we calculate that out, we end up with a final answer of 2,035,800 different ways. So let's see how we could figure these out using factorials in the formula. So it looks like in example 3a, we started off with 11 factorial, right? We divided it by this, which is 3 factorial. And then what else did we get rid of that was canceled out from the top? Well, see how we stopped at 9? That means that the 8, 7, 6, 5, 4, 3, 2, and 1 got canceled out. So on the bottom, we must have also divided by 8, 7, 6, 5, 4, 3, 2, 1, which is 8 factorial. So that's the formula. It would have given us 165. The way to write it in the formula that looks like that would be NCR. The N is the number to begin with, then the C, and we were choosing 3 of them. So you could type that in your calculator. The way to get to that is to type in the N first, whatever your number is. In our case, it would have been 11. And then you would press math over to probability, and then you'd pick option 3, and then you'd get the NCR to show up on your screen, and then you would type the R, which is 3, and it would have given you the answer. On 3B, we would have had 30 factorial on top. On bottom, we had 7 factorial to account for the fact that it didn't matter the order we were choosing our 7 students, and then we'd have to get rid of the remaining numbers we didn't get to, which would be 23 factorial. Or we could write 30 C7. Last, hopefully you can think about whether the order matters or not on these last 4 questions. If you pick 5 apples from a basket to eat, it doesn't matter the order, so that'd be a combination. If you're picking specific jobs for people, that's a permutation. If you're picking representatives where everybody's equal, that's a combination. And if you're awarding first, second, and third place in a race, of course it matters who gets gold, silver, and bronze, so that's a permutation.